In today's lecture, we're going to talk a little bit about causality and how we can think about studying causality in the social sciences. So, the first thing I want to do is I want to talk a little bit about a framework for thinking about causality, where we think about 5 possibilities that could exist if X is correlated with Y. So, what we're doing here is we're trying to think about whether or not there could be a causal relationship between 2 variables that I'm calling X and Y. Those 2 variables could be anything. But for an example, let's think about the potential relationship between a pay for performance system and productivity. Now, what I mean by a pay for performance system is some sort of pay system where you decide to pay employees more money if they perform well. So, for example, some teachers in certain school districts are paid a bonus if their students perform really well on standardized exams, or if they maybe they're taking into account other measures like how satisfied are parents with the schools, but somehow performance is measured, defined, and people are paid bonuses based on that. This is a model that is used in lots of different sectors, both in the public and the private sector, and lots of different types of organizations. So we're going to think about the potential effect of pay for performance, which would be our X variable, on productivity of employees, which would be our Y variable. So if we find that there's some correlation between them, that perhaps employee productivity is higher within our sample in organizations that are using pay for performance, that would be a positive correlation between X and Y. If we find that there's a positive correlation between these 2 variables, we can think about 5 different reasons that there might be that positive correlation. So the first one would be that maybe the correlation between X and Y is just a coincidence. We're going to talk about each of these possibilities in more detail in just a moment, but let's go through all 4 quickly. So first possibility is a coincidence. Second possibility is that there's some third variable that causes both X and Y. Third possibility is that maybe Y causes X instead of X causing Y. A fourth possibility could be that there's some sort of research design problem, something like we're measuring our variables incorrectly. And a fifth possibility is that X causes Y. That's usually the conclusion that we want to jump to. But in order to be able to conclude that X is causing Y, normally we want to be able to somehow rule out, or at least tentatively rule out, the other 4 possibilities. So as you can already see from my just limited discussion of this framework, assessing causality is a bit like detective work. We're going to have to use the process of elimination and think about different causal processes or different reasons that X could be correlated with Y. And doing good research, or good assessments of causality based on data uses a set of skills that requires you to sort of think creatively, think analytically about different possibilities, and be able to rule out alternative explanations for why you might be seeing what you're seeing. Again, as I said, generally, if we can rule out options 1 through 4 and we're seeing a correlation between X and Y, that's going to give us the ability to conclude that 5 must be the case, that X is causing Y. Although sometimes we reach that conclusion tentatively, depending on how much certainty we have that we can rule out possibilities 1 through 5. Sometimes we have a high degree of confidence that 1 through 4 are not the causes of the correlation between X and Y. And so because of that, we would say that we have a high level of confidence that X causes Y. So let's go through each of these possibilities, like I said, in a bit more detail. So the first possibility is that the correlation between X and Y is just a coincidence. The main tool that we're going to use to assess this is one that we've already been talking about in this course, the tools of statistical inference. And in particular, we have 2 tools that we've been talking about: confidence intervals and hypothesis tests. And as we know, those allow us to see whether or not a relationship is strong enough that it's bigger or stronger than we would expect just from dumb luck. Part of the reason that we worry about there being a coincidence that would cause X and Y to be correlated is we know that there's always randomness in our data. Randomness might be a bit of a term of art because there's almost always some cause of whatever we're observing, but it's a cause that we can't necessarily measure or quantify that's going to cause some of our variation. There's going to be unpredictable things, uncertainty. And if those factors are just leading to patterns that we can't really explain, that maybe we wouldn't find again if we went back and reconducted the study, then we would say that those factors are sort of random. We could describe them as randomness. Another way to think about this is that almost any time I calculate a correlation between two variables, I'm going to get a non-zero value. Now, sometimes I'll get a correlation that's very close to zero, maybe something like 0.13 or 0.025. Those would be very small correlations, but they're still not quite zero. And the reason is that it's very unusual to get a data set where two variables have a correlation of exactly zero. So often we're not talking about whether or not there's a correlation, but how strong is that correlation? And is that strong correlation stronger than what we would expect just from dumb luck, just from coincidence, if X and Y in a perfect world where we had no noise, no randomness, where their correlation might actually be equal to zero. In other words, if the two variables are truly unrelated to one another, we would say their true correlation is zero, but we might still get a non-zero value. We usually would get a non-zero value of the correlation in some finite sample that we observe because of randomness that sort of pushes the observed correlation around one direction or another. The next, I'm going backwards through the slides, pushing the wrong button. Here we go. The next, another way we can think about this is that when we do a hypothesis test, we're asking if the correlation is statistically significant. Generally, if we say it's statistically significant, what we sort of mean is that we're ruling out possibility one. So you've sort of already learned how to deal with this first possibility. You want to look at a confidence interval or at a hypothesis test to see, is this correlation something that we're confident is non-zero, even after accounting for noise, even after accounting for some uncertainty due to the fact that we're creating an estimate. So if we take this back to the tangible example of a pay-for-performance program, if we have a sample of maybe 100 organizations and 50 of them have implemented pay for performance and 50 of them have not, if we find that the ones that have implemented pay for performance have a slightly higher level of productivity on average, we might wonder, well, is it just a coincidence, or is that difference in productivity big enough that it's more than what we'd expect from just random noise? Is it big enough that we would say that it's statistically significant, and therefore we can sort of rule out, at least with some degree of confidence, possibility one? Can do a similar thing with confidence intervals. As we've already learned, confidence intervals and hypothesis tests are really just two sides of the same coin. With a confidence interval, we're going to be looking at, does that range of possible correlations include the value of zero? Or can we conclude that it must be a positive relationship or that it must be a negative relationship? All right, what about possibility two? Possibility two is that some third variable, which we're calling z, causes our two main variables. The main tool that we're going to use to try to address this concern is something called multiple regression. And that's not a major focus usually of an intro statistics course like this one. But depending on your curriculum and what you plan to take next, if you take another statistics course, there's a good chance that you'll go a lot deeper on multiple regression. Multiple regression is like simple regression that we've learned, or linear, well, it's still a form of linear regression. Bivariate regression is what we've been doing. Multiple regression is where you have multiple independent variables simultaneously. So we would do something like try to predict values of y based on both values of x and values of z simultaneously. And that's going to help us to be able to address this possibility. The basic idea behind why we care about this is that generally, if z has an effect on both variables we care about, x and y, x is going to be correlated with y because of that common effect of z, even if x has no causal effect on y. So one thing we could think about is maybe there's something like organizational prestige, right? There are some organizations that are very attractive to work at. They're sort of known to be the best employers in the industry, and other organizations maybe are considered a bit more boring to work at. Well, you might imagine that organizational prestige is going to attract very motivated workers, and so they're going to have very high levels of productivity. In other words, prestige Z is going to be correlated with productivity Y. It's going to cause Y. Well, prestige might also have an effect on the practices of that organization, including their pay practices. Maybe it's considered a trendy thing to pay for performance. So, prestige is also causing organizations to adopt pay for performance. Well, in this case, we would see a correlation between pay for performance and productivity. But what's causing that correlation is the fact that prestigious organizations are both attracting talented workers, productive workers, and also prestigious organizations are following the trend of adopting pay for performance. That would be an example of how a third variable can cause a correlation between X and Y. When we're using multiple regression to try to control for this, like I said, we'll often use the word control, controlling for the effect of Z. And this slide shows some code you can use to run a regression with two independent variables in stata. If X has a statistically significant coefficient while controlling for Z, then we would typically say, well, we can rule out possibility 2 at least tentatively. Now, one difficulty with actually being able to do this in practice is that we're only able to conduct a multiple regression and rule out the potential spurious correlation or the correlation that pops up because of some third variable if we're able to measure that third variable. In other words, if we have some variable Z, but we're not able to measure it, then we're not easily going to be able to use multiple regression to be able to rule out the possibility that Z is causing both X and Y. So we're limited by what we're able to measure. It also could be that there's several Z variables that could be potentially confounding the relationship between X and Y. And so we need to be able to get measures of all of those variables. And oftentimes people, no matter what list of variables you've gotten, your audience, if you're presenting research, for example, can always think of another Z variable that you're not able to measure, no matter how many you've already done. And so this requires a lot of care. You have to think carefully about what variables might cause this sort of relationship that might be affecting both your independent and dependent variable. And then you have to be very dedicated to going and hunting down measures of those variables. So some people are skeptical of this approach to trying to establish causality because they think there's always going to be some Z variables that you might have missed. All right, let's look at possibility 3. Possibility 3 is that Y causes X. The tools to address this are going to be beyond the scope of what we're going to talk about in this course, but sometimes you can just use logic to sort of rule out this kind of thing. Now, in our case that we just talked about, this would definitely be a potential problem. What if organizations with higher productivity decide to adopt pay for performance because having productive workers somehow induces them to adopt this pay policy? That could certainly be the case, particularly if productive workers are ones who like pay for performance policies because they know that they're going to perform well. And so they push management, push their employers to do this. That's certainly a possibility here. We might think, though, about something like the relationship between age and who someone decides to vote for. In this case, Y would be our dependent variable. Y would be who someone votes for, and X would be their age. In this case, we could logically rule out the possibility that who someone votes for is causing their age. Of course, age is not something that can be changed by someone's attitudes or by their choices. Age is just something that's sort of a fixed characteristic. And so because of this, we would be able to rule out the possibility of Y causing X with a research question like that. But with many research questions, this is a concern that you might have to worry about. Sometimes if you collect data at multiple points in time and sort of track how things move over time, that can help you address this question because maybe you can see a change in X that precedes a change in Y. And so that'll give you some reason to believe that X moves first and then Y follows it. But those sorts of research designs tend to get a little bit more advanced. So we'll save that for a future class. All right, what about possibility 4? Possibility 4 is sort of an umbrella category that I've termed research design problems. It could involve lots of different things like measurement error, that you somehow sampled wrong, something called self-selection, which would be that maybe individuals are selecting into organizations, and certain types of people are attracted to organizations with pay for performance. So maybe you're observing the effects of selection when you see a correlation rather than seeing whether or not that policy serves to motivate the people that you already have there. Another possibility is attrition, which means that some people are dropping out of your study and you don't collect data on everyone. Maybe you observe a relationship between two variables, but the independent variable is actually causing people with certain values of the dependent variable to drop out of the study rather than changing the values of the dependent variable. There are lots of issues, and there's a lot more that we could say about research design. Here's another example of the self-selection issue. We might see that one hospital has better health outcomes than another hospital, and we might think that means that hospital is doing a better job. Maybe we find that the hospital is larger, and so we think that size is positively related to health or the performance, the health outcomes from that hospital. But in fact, it's actually the case that healthier people are self-selecting. They're choosing to go to that hospital, and therefore we don't observe this relationship because of size. It's not that size is causing the hospital to be higher quality. Instead, it's that healthier people are selecting to go to this hospital, and that's why we're observing better health outcomes. So maybe we need something like a before and after design where we can see how healthy people are when they enter the hospital and then track, did their health improve or decline during the time that they were in the hospital. Research is not easy. There's going to be lots of mistakes that we can make. And so a lot of what we do when we study research design is try to rule out various problems that could creep up and cause a correlation to exist between two variables that might not actually reflect the causal relationship between those two variables. All right. Again, if we are able to rule out those first four possibilities, that's going to help us conclude that it is likely that X is actually causing Y, assuming that we've found a correlation between X and Y. Often experiments, or sometimes what people will call quasi experiments, are going to be used to help out rule out possibilities 2 through 4. When we say a quasi experiment, we mean that the researcher didn't necessarily manipulate the independent variable, but maybe they saw something happen out in the world that mimicked the type of experiment that a researcher might set up if they were to design it themselves. With experiments, we often do something called randomization, where you maybe flip a coin to figure out who gets the treatment and who doesn't. We see this in medicine a lot of times. You could imagine an organization that says, or a set of researchers that partners with a bunch of organizations. And if they could somehow get those organizations to agree that they were either going to use pay for performance or not use it based on whether or not a coin came up heads or tails, that would provide a really good research design. Now, for obvious reasons, a lot of organizations wouldn't be willing to set their pay policies based on a coin flip. But if one was able to do that, it would really create a strong research design to assess causality, because you could easily rule out possibilities 2 through 4. The reason you could do that is because X is being caused by the coin flip that the researcher has conducted. So we know that there's not some third variable Z that's causing X. We know that the dependent variable, productivity, isn't causing X, or isn't causing the adoption of the pay for performance problem. And if we've designed the research program well, we know that we're not going to be subject to some of these research design problems that we worry about if we have data that wasn't collected in an ideal way. So randomized controlled trials are very popular these days, and a lot of the reason they're so popular is because they give us a really good set of tools to try to rule out some of the reasons that two variables might be correlated that would be other than the causal relationship we're interested in understanding. There are lots of fancy techniques aside from experimentation that are being used these days more and more by economists and different types of policy analysts, but those are sort of beyond the scope of what we're going to talk about in this class. All right, a few important concepts that I want to talk about before we end this first video from this lecture, and then we'll have an example in this second video in this lecture that you'll be able to look at. So the first concept we want to talk about is there's this term that researchers use called internal validity. Internal validity is a word that refers to how confident we are that there's a causal conclusion that we can reach based on our study. So in other words, it's asking how much certainty do we have that that fifth explanation that X causes Y is the conclusion that we should reach. External validity is a different kind of confidence. It's asking about how confident are you that the findings from your study can be generalized to other settings. So in other words, maybe I have a study of 100 organizations. External validity questions are going to be about, well, based on what I saw in these 100 organizations, is it going to tell me very much about other organizations? Maybe I've studied one state and the unemployment agencies in that particular state, maybe Colorado. External validity would be concerned with questions like, is what I learned from this study in Colorado going to help me understand how organizations work in Oregon or in Nevada? Two other terms we want to know are experimental studies and observational studies. I already referred to experiments a moment ago on the last slide. Experiments, what we mean by that formally when we say experimental studies, is a study where the researcher has manipulated one or more of the variables of interest. And usually, or those are always going to be independent variables. So rather than just seeing which organizations have adopted pay for performance and which ones haven't, the researcher is going to be involved in actually telling certain organizations to adopt pay for performance or not. Again, a classic example of an experiment is when you're testing out medications and the researchers say these particular patients are going to receive the actual medicine and another set of patients are going to receive sugar pills or some sort of placebo. By contrast, an observational study is often what we see in the social sciences, and that's where you just go out and measure variation in variables that's happening naturally in the world. So something like someone's age, someone's gender, someone's race, those are things that we're not going to be able to experimentally manipulate because we can't just go and change those characteristics of an individual as a researcher. So we're going to have to rely, if we want to study the effects of those variables, on observational studies, where we're going to go and observe some people who have certain characteristics, other people who have other characteristics, and then try to understand what the effects of those variables might be. All right, that's it for video 1 in this lecture. Like I said, we'll walk through an example of how to use some of these tools in part 2 of this lecture.